So here's a really interesting kinematics problem that was actually given in one of the physics Olympiads sometime between the 1960s and the 1980s. And you can actually find this problem in Krotov's book called Aptitude Test Problems in Physics. So this is the kind of thing that you would probably get as a student who's sitting the physics Olympiad, or you might actually get this in university if you're studying rigid body dynamics. And if you like to see something like this in the future, or if you have any suggestions for any topic or any specific problem that you'd like to see on the channel, feel free to let me know in the comments. So let's read this problem and let's see what it wants from us. So we've got something called a bobbin, which is essentially a cylinder or a circle with two different radii, and you've got this thread which is wound on the circle with a smaller radius. And then this thread runs all the way from the bobbin all the way to this nail, and it goes around the nail. And the thread is being pulled downwards with a certain velocity v. And what we have to find, knowing all this, is what is the velocity of the center of the bobbin, okay? In the moment when the thread and the vertical make an angle alpha. So let's call the center of the bobbin C, and I also called this point here, which is in contact with the ground, I named it O, right? And another key thing that's happening is that the bobbin rolls over the horizontal surface without slipping. So because it rolls, this is actually a hint, and it actually tells us that the direction of the velocity of point C, of the center of mass, or just the geometrical center, is going to be in the horizontal direction. Okay, and without losing any generality, I'm going to assume that that velocity at point C is going to be to the right. Okay, and I'm going to call this VC with an arrow because this is a vector, obviously. Okay, now let's try to understand what's happening with the thread. So as the thread is being pulled, right, first of all, the thread is inextensible, which means that if I pull on the thread with a velocity v downwards, then every single point on this thread is going to have the same velocity v, right? Um, Now, obviously, this velocity v is different from this velocity v simply because the direction is different, but their magnitudes have to be the same. If the magnitudes are not the same, it means that the thread would extend, which is not the case. Now, this also means that this point here on the bobbin, which is in contact with the thread, will have a velocity v going this way, like that, right? Which tells us that this point, which is sitting on the thread, which is tangent to the small circle, has a velocity component along the thread, which is equal to v, right? Note this is not actually the absolute velocity at point P, it's just the component in the direction of the thread. So with this in mind, let's try to see how we can find the velocity of point C, okay? And we'll take it step by step. So first of all, I'm going to try to write the velocity of point C based on the fact that there's no slip. So I'm going to use Euler's equation for velocity for that, which tells us that the velocity of C is equal to the velocity of O, and then plus omega cross product with the position vector of C. Okay, and when I do that, I have to put my coordinate axis into point O, so I have x and y like that. And we know VO, right? We know that this is 0 because there's no slip, which will give us VC equals omega cross OT, right? And this is a determinant. So this is going to be I, J, and K. And then again, I don't know what direction omega has, but by default, I'm going to consider it to be positive. And then OC is the position vector of point C with respect to O. And that's just capital R, right? That's what the problem tells us. It's this R right here. It's capital R and it only has a J component because it's purely in the Y direction. So with this in mind, we can actually find what the velocity of C is. So it has only an I component and the value is going to be minus omega r, and that's it. Now, obviously, we haven't solved the question because we don't know what omega is. So we have to find omega through another route and then come back, use that value of omega, put it in here, and then we will be able to find what the velocity of the center will then be. So let's think how to actually do that. And what I'm going to do now is I'm going to draw the inner circle. So this is point C, as I called it previously, and then this is the outer circle, which I'm not going to draw the entirety of it, but just part of it will be fine just to give us some measure of perspective. And then this here is going to be my point P, and then I've got my V component of the velocity of point P, which is here. Okay, now if we have a look what's happening on this diagram, there's one thing that we have to calculate, which is this angle, right? Now the question tells us this angle is alpha, and using trigonometry, we can actually, well, using geometry rather, we can actually see that this angle here is going to be equal to 90 degrees or pi over 2 minus that angle alpha. Okay, so I'm going to write that as pi over 2 minus alpha, and we're going to use that to find the velocity of point P. Okay, now the other thing to note is that to make things as simple as possible, I will use a coordinate system which is tilted. So in other words, I will use an xy coordinate system, but the x-axis is such that it actually goes along the direction of the thread. Okay, and you'll see why we do this. So what I'll do now is I'll use Euler's equation again. So I'll write that the velocity of point P, right? That's the velocity that we don't know it. We just know that the component along the thread is V, which is given to us as the same V as this one here. So we've got Vp is equal to Vc, and then we have plus omega, which is what we're trying to find out, and then cross product with Cp. That's the position vector of P with respect to C. Now I'll take this to the next page actually, and we will see what we're going to get. So the velocity of point P, we're going to say that the velocity of point P has two components. It has this component, which is along x, which we know. So I'll write v times I, right? That's the velocity in the x and the in the x direction, which corresponds to the unit vector I. And we also have a velocity normal or in the radial direction, which has the j unit vector associated with it. And this equals to Vc, which we're going to come back to in a second, plus, and then we have our determinant, which is I, j, k, and then omega is what we're trying to find out, and it's only having a z component, and then Cp. So Cp only has a y component because it's measured from here to here. It's the position vector that goes from C to P, and its value is equal to small r, and the sign is negative because it goes against our positive y direction, and then we have 0. Okay, so this gives us that v times I plus the normal component times j. Now you'll notice that we don't actually need to calculate this, and you'll see that in a minute. Now this is Vc plus I multiplied with, so if we do this determinant, we're going to get omega r. Okay, so the only thing left is this Vc right here. Now you might be tempted to just put the value of Vc that we got here, which is minus omega r, but it's not really correct because when we did it here, we used a coordinate system with x going to the right and y going up. So the velocity of c that we got is actually equal to, well, is actually this red arrow, which I'm going to call Vc. Okay, so now we actually have to find the components of Vc along the new x direction and along the new y direction. Okay, and what we have is the following. So this angle here, this angle here is the same as this angle here, which is the same as pi over 2 minus theta. So this angle is pi over 2 minus or minus alpha. And then this is equal to Vc, and instead of Vc, I will write what Vc actually is, which is minus omega r. So minus omega capital R, and then we're looking at the cosine of this angle. So we have cosine of pi over 2 minus alpha, and this is along the x direction, so we need an I multiplied with it, and then plus, and then we take the y component, which is minus omega r, and then we have sine of the same thing, and then this is multiplied by j. Okay, and to that we have to add, and I'll just add it here on the left, we have to add I times omega r. Okay, and this is equal to this. So this goes on the left-hand side of the equation. So it's a pretty long equation, so let's try to simplify it a bit. So on the left, we have Vi plus Vn times J, and that is going to be equal to, so we have I multiplied by omega small r. Now, this here, this cosine of pi over 2 minus alpha, according to trigonometry, this is actually the same as sine alpha. And sine of pi over 2 minus alpha, this is equal to cosine alpha. So we're going to use that to our advantage to simplify the equation a bit more. So we're getting I omega r, and then we have minus omega capital R, and then we replace the cosine with sine of just alpha, and then that's multiplied by I, and then we've got minus omega r, I'll write it here, and that is cosine of alpha j. Okay, so we've got one equation, but it's actually two equations in one here, right? Because we look at the I, we look at the x and the y component separately. So what we have now is that the x component on the left has to be equal to the x component on the right. So the x component on the right is this and this. So if we separate that, we'll have that v is equal to omega r minus omega capital R sine alpha. And from here, we can just find omega because this is one equation with one unknown, right? It's, omega is the only thing we don't know. So if we write v as omega, we factorize it. So this will be small r minus capital R sine. So omega is v over small r minus capital R sine alpha. And that's the angular velocity of the spool, right? We're not done yet, we just have one more step to go. So remember, the question was asking us to find the velocity of the center of the spool. But we have an expression for that already, and it's this one, right? So we have that the velocity of the center of the spool was I times minus omega capital R. So this is the value that we're looking for. So the velocity of the center of the spool is minus omega r. If we cancel out the I, if we turn this into a scalar formula, so this will be minus omega is what we got on the previous page, so it's just minus v over small r minus capital R sine alpha, and then times r. Okay, and what I'll do now is I'll take this minus and I'll put it in the denominator. So finally, the velocity of the center of the spool will be Vr over R capital R sine alpha minus small r. And the nice thing about this is you can actually see that this holds from a dimensional point of view. So if you get something like this as your final result, you can actually rewrite it as v in front of the fraction, and then you just have r over r sine alpha minus small r. So you have that a velocity is equal to another velocity times this fraction, which has no units, which makes sense from a dimensional standpoint at least. So this is one way to actually check whether you got the right answer if you have to do something like that. So yeah, that's the question using Euler's formulas.